Hello, in this video we will go over application and computer graphic and how it's related to transformation. So this is linear algebra and we are going to we're going to learn about applications to computer graphics. So basically what we have learned so far were matrices and we can use those matrices uh, for computer graphics. So what is computer graphics? Computer graphics is everything except text and sound, such as geometric modeling, image rendering, animation, simulators for flight or driving, CAD programs, architectural visualization, and virtual reality. So let's go real simple. So let's start with the letter N. Uh, here's a letter N, and then you have all these points, right? We can use those points to put it into matrices. Then what we have to do is sometimes we're gonna have to move the N to the right, move it to the left, or you could flip it right, flip it, make it bigger, smaller. So that's what we're gonna do. It's called so yeah, we figure out all the points on that letter and then we use transformation. And for what do I mean by transformation? We can either contract, expand, meaning scale. We could do a reflection, we could do a shear, we could do a rotation, and we could do a projection and a translation. So those are all transformations. Okay, so let's talk about contraction and dilation. So if you recall, dilation makes it kind of bigger or smaller, right? So here we have a 2D point or an XY. And to do a contraction, it's going to be K0, 0, 1. It probably doesn't all make sense, but when I do an example, you'll see. Or for a dilation, you would set it up as this matrix 1, 0, 0, K. And how do I know this is an XY? Because this is your X, this is your Y. So we're still in technically 2D. And yes, we can go 3D if we want. So what about rotations? You can do a rotation if you set it up like this, cosine theta, sine theta, negative sine theta, cosine theta. Okay. So just go ahead and write that down on your notes. Okay, for a shear, for a horizontal shear, you're going to set it up like this, 1, 0, K1. And for a vertical shear, you're going to set it up as 1K, 0, 1. Okay. What about projections? So if it's projected onto the x-axis, you're going to set it up like this, 1, 0, 0, 0. Or if it's projected on the x2 axis, you're going to set it up as 0, 0, 0, 1. Okay. What about reflection? So there's quite a few reflections. So there's a reflection over the x1 axis. You would set up like this, 1, 0, 0, negative 1. Reflection over the x2 axis, it would be negative 1, 0, 0, 1. Through x2, x is script 2, x1 is going to be 0, negative 1, negative 1, 0. So these are, yeah, these either make these zeros. Through the origin, you're going to set it up like this. This diagonals are 0, and then this is negative 1, and then this is negative 1. Okay, homogeneous coordinates. Homogeneous coordinates, each point x comma y in R square can be identified with the point x comma y comma 1, meaning 3D, meaning x, y, and z, on a plane of 3D, R cubed. So let's say you want to go from a 2D translation of 2D to a 3D. So converting a 2D to 3D, you would set it up like this. So this would be 2D. This is your x, this is your y. And then 3D, you would set it up like this. This is your x, this is your y, this is your z. So 1, 0, 0, 0, 1, 0, 0, 0, 1. And we can do translation. So if you want to move it horizontally, H moves horizontally, you just do a plus H. And you could do a vertical translation, K moves vertically. Okay, so you have X, Y, 1. So what you would do is write, okay, so this is like the next thing we have to learn. Uh, when you do translation, it's kind of like the reverse order. We're going to multiply from left to right, but we're going to write it from right to left. It's kind of backwards. So for example, X, Y, 1, and you want to do a horizontal shift, a plus H, and a vertical shift, a plus K, and then this stays the same. You would write it out as these two matrices, 1, 0, 0, 0, 1, 0, HK1, 1, 0, 0, 0, 1, 0, 0, 0, 1. So you'll see what I mean in a bit. So composite translation basically is two or more basic transformation formed by multiplication of matrices. So it's yeah, what we're doing is you do the reverse order, right? Uh, we're going to multiply from left to right, but we're only going to write it from right to left, if that makes sense. So you start with the first transformation, put it on the right, uh, or first transformation on the right matrices, second transformation on the going left, and then the last transformation goes to the further left. It's like reverse order, right? We are going to multiply from left to right, but we are going to write it from right to left. Okay, so let's do an example. Example 1, given the following coordinates vectors 2, comma 3, 4, comma 3, 3, comma 5, find the new uh, coordinates, find the new coordinates. And this is in 2D, so we're not converting it to 3D, just 2D. So we want to reflect it over the y-axis. So two is your this two is your x, this three is your y, this four is your x, this three is your y, this x is your three, this three is your x, this five is your y. So if we're going to reflect it over the y-axis, these numbers are we can write that as a matrix. These it would be 2, 3, right? This is your x, this is your y column row, this is your x row, this is your y row, and then keep on going. So the next x is 4, the next y is 3, the next x is 3, the next y is 5. Okay. And then we go from left. And then if we're going to reflect it over the y-axis, you're going to multiply because we went over the rule. If the reflection over the y-axis is going to be, you're going to multiply this by negative 1, 0, and 0, 1. That was the rule we just went over. And when you multiply out those two matrices, you're going to get this new matrices, -2, 3, -4, 3, -3, 5, right? Okay, so what that means is this is actually can be expressed as coordinates. So your new coordinates can also be expressed as -2, 3, -4, +3, -3, 5. Now, is that true? According to, if you had coordinates, what is the rule of reflection across the y-axis? You make the x negative, right? So compare the old coordinates with the new one. Yes, that's right. 2, 3 is now -2, 3. 4, 3 will now be -4, 3. 3, 5 will now be -3, 5. So that's totally true, right? So this is really cool how you can use matrices in 2D or 3D um, to get a new matrices that's reflected over the y-axis. Okay. Okay, let's do part B. Part B says reflected about the origin. So I kind of did this one already. So this is our original matrices. These came from our coordinates. Uh, Going vertically, so this is your x row, this is your y. So 2, 3, 4, 3, 3, 5. And then according to the rule, reflection of the origin is this matrices. This matrix, -1, 0, 0, -1. And then when you multiply that out, you should get, I read it already. No, you should get this. -2, -3, -4, -3, -3, -5, right? And that makes, if you want to express this as a coordinate, it can also be expressed as a coordinate. So this is your x row, this is your y. So this would be -2, -3, -4, -3, -3, -5. Okay. Okay, what about the vertical shear of 3? So start out with your original matrices. It was 2, 3, 4, 3, 3, 5. And then what is the rule for vertical shear of 3? It would be this matrix, this matrices. 1, 0, 3, 1. And you multiply it out, you get this. 2, 4, 3, 9, 15, and 14. And yes, you can express this as a coordinate. It would be 2, 9, 4, 15, 3, 14. Okay, let's do another example. Example 2 says, given the following coordinates vectors, 2, 3, 4. I think this is the same one. 2, 3, 4, 3, 3, 5. Find the uh, new matrices in 2D, or the coordinates as well. So see horizontal shear. So start with your original matrices or your original coordinates. It was 2, 3, 4, 3, 3, 5. And then for a horizontal shear of 3, it would be this. 1 here, 3 here, this is a 0, and this is the 1. And when you multiply those two matrices, you get this product. This matrices, 11, 13, 18, 3, 3, and 5. Okay. Then if you want to express it as a coordinate, it could be expressed as 11, 3, 13, 3, 18, 5. Okay. Okay, what about a rotation of 30 degrees? To start with your original coordinates. So our original coordinates was 2, 3, 4, 3, 3, 5. And then what is the rule for a rotation of 30 degrees? It is this. It was, this would be cosine, and then whatever your degree was, ours was 30. The cosine of 30 degrees, sine of 30 degrees. This would be negative sine of your degree, 30 degrees, and then cosine of 30 degrees. So if you recall in your trig course, cosine of 30 is square root of 3 over 2, and sine of 30 is positive 1/2. So let's fill this in, and before we multiply out the two matrices, it would be, okay, so cosine of 30 is radical 3 over 2. Sine of 30 is 1/2. Negative sine of 30 is negative 1/2. Cosine of 30 is radical 3 over 2. And this stays the same. And when you multiply out those two matrices, this is what you get. Zero point 0.232, 1.964, 0.981, then you have 3.598, 4.598, 5.830. And if you want to write it as a coordinate, as a 2D coordinate, it would be as this. Okay, what about F, projection onto the x-axis? Okay, start with your original coordinates. Our originals were 2, 3, 4, 3, 3, 5. And then the rule for projection onto the x-axis is this. It would be 1, 0, 0, 0. And when you multiply those two matrices, you get 2, 0, 4, 0, 3, 0. And if you want to write it as a coordinate, it would be expressed as 2, 0, 4, 0, 3, 0. Okay. Okay, let's do another example. So an example, this one says find a 3x3 matrices, a 3x3 matrix, singular, that produces the described composite 2D transformation using homogeneous coordinates. So what we have to do is first we got to translate. So I kind of did this one, translate by -2, 3, and then scale the x coordinate by 0.8 and the y coordinate by 1.2. Oh no, I didn't actually do this one. So yeah, so what we're going to do is first is make this into a 3D, right? We had an x comma y. Now let's make it into 3D. X, Y, Z, and then my Z is 1. I think Z is 1 is because we're not going to touch it. So your two matrices, so the first would be this. So we always start from the right and move our way to the left. So it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is our first. We're going to translate it. And then we're going to scale it. Okay. So then what we're going to do is we are changing what we want and giving the opposite order. Let me write that down. We are changing what we want and going opposite order. Okay. So, uh, so, so we said that we're going to translate it by the coordinate -2, 3. So this matrix will be 1, 0, 0, 0, 1, 0, and we said our x, we're going to translate from -2, 3. So this is now going to be -2, and then this 0 is now going to be +3, right? And then, so remember, this is your x row, this is your y row. That's why this is a 3, this is a -2, right? And then the second step, we're going to scale the x coordinate by 0.8 and the y coordinate by 1.2. So this new matrix would be 0.8, 0, 0, and then this is going to be 0, 12, 0, 0, 0, 1, right? So this is your translate first, and then this is your scale second. So when you multiply those two matrices, you get this new matrix 0.8, 0, -1.6, 0, 1.2, 3.6, 0, 1. Okay. Let's do another example. Okay, so this other example says, find a 3 by 3 matrix that produces the described composite 2D transformation using homogeneous coordinates. So x, y, and we're going to 3D, x, y, 1. We got to rotate the point 60 degrees and then reflect it through the x-axis. So what we have to do is first, you got to do a transformation. Rotate points 60 degrees. Then what we got to do is reflect it through the x-axis. So our first matrix would be 1, 0, 0, 0, 1, 0, 0, 0, 1, and then this one would be 0, 0, 0, 1, 0, 0, 1. Okay. So then what we got to do is first rotate. So this would be cosine of 60 degrees. 60 minus sine of 60 degrees. And then this is 0. And then this would be sine of 60 degrees. Cosine of 60 degrees is 0. And then this is 0, 0, 1. And I believe this is this is our rotate. So remember, we go backwards. This is our first commandment. We got to rotate it and we start on the right-hand side. And then our second commandment was a reflection. So this is the matrix for a reflection. Okay. Okay, so when you multiply these two matrices, it would be 1, 0, 0, 0, negative 1, 0, 0, 0, 1. So why is this now a negative 1? Because we said that we were going to reflect it across the x-axis. So remember, this row is your x, so that's why I made this a negative 1. And then we should figure this out before we multiply these two matrices. So cosine of 60 degrees is positive 1/2. Negative sine of 60 degree is negative radical 3 over 2. This is 0. And then sine of 60 degree is radical 3 over 2. Cosine of 60 degree is 1/2. 0. And then this is 0, 0, 1. Okay. And when you multiply out those two matrix, you get like 1/2 negative radical 3 over 2, 0, negative radical 3 over 2, negative 1/2, 0, 0, 0, 1. Okay, let's move on to the next example. So the next example says, find a 3 by 3 matrix that produces the described composite 2D transformation using homogeneous coordinates. Given the point 0, 5, calculate where the point would be after rotating points at 45 degrees about the point 3, 7. So first we're going to do is it was 2D, right? So we were given the point is 0, 5. And we got to make that into a 3D. So in 3D, it would be expressed as is 0, 5, 0. So this is your x, this is your y, this is your z. Y is z 0 because we're not moving z, right? Z is not moving. So first I gotta rotate, and we're gonna put that matrix on the right, further right-hand side. So first rotate 45 degrees. Then we're gonna do a translation, and we're gonna put that matrix on the further left of 3,7. Okay, so first is rotation of 45, and we said that we're going to put that matrix on the further right. So that would be cosine of 45 degrees, negative sine 45 degrees, sine 5 degrees. Oh, keep in mind we are going to make it in the 3D, so this z is going to be 0, and this is going to be cosine 45 degrees. This is going to be 0, and then this is going to be 0, 0, 1. Oh, also, we remember we were given the point 0, comma 5 in 3D, so we're going to put that on the further right, right? So first we translate it into a 3D. So that's why this matrix is on the further right. Then what we did is we're going to do a rotation. So this is why this is the next matrix going to the left. And then the last matrix to the further left is translation of 3, comma 7. So this matrix would be expressed as 1, 0, 3, 0, 1, 7, 0, 0, 1. Okay, so recap, we do our first commandment and we put that matrix on the first right. So the first commandment was the given point, or the first translation. The second commandment was a rotation. And then the last commandment was a translation. Okay, so let's see. So this matrix stays the same. This one you can do your algebra. What's cosine 45? It is radical 2 over 2. What is this sine of negative sine of 45? It is negative radical 2 over 2. This is 0. And then what is this sine of 45? It is square root of radical 2 over 2. The cosine of 45 is square root of 2 over 2, 0. And then this is going to be 0, 0, 1. And then this one, I think this stays the same. Okay. So when you put all that together, you get this matrix. This one. When you multiply it out, I think, yeah, it's going to be this. It's going to be your x coordinate will be negative 3.535. Your y coordinate will be 3.535. Your z coordinate will be 0. Okay, so you started with 0, comma 5, and then you ended with negative 3.53, comma 3.535. Now I'm going to end the video with something called the perspective projection. So yeah, let me go over that. So one more thing we have to learn. So yeah, perspective projection, 3D object. So a perspective projection is a 3D object is represented on a 2D computer screen by projecting the object into a viewing plane. For simplicity, we let the XY plane represent the computer screen, and then the eye of the viewer is along the positive z-axis, 0, 0, D. So a perspective, yeah, so 0, 0, D. So where was I? So yeah, so a perspective projection maps each point XYZ onto an image of the point X, Y, comma 0, so that the 2 points and the eye position center of the projection are on a plane. Uh, so what you want to do is pretend the computer screen is the XY plane, and the observer, meaning you, the observer weighs the eyeball, weighs the eyeball you, and you're sitting back. The computer screen or the board is the XY plane, and you observe are a certain distance from the screen, right? So here's like a little image of what's happening. This point here is your eyeball, and this point here, yeah, this is your eyeball, this is the screen. So write this down in your notes. So x star is x over 1 minus z over d, and then y star is y over 1 minus z over d. So you're using homogeneous coordinates, x, y, z, 1. Uh, x is x over 1 minus z over d. Y is y over 1 minus z over d. Z is 0 because it's flat, and x, y, x, y, z, and then this is your d, or this is 1, yeah. So prospect matrix, it's basically this 1, 0, 0, this matrix. Okay, so you start at the right hand side, x, y, z, 1, and then this is going to be 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, -1/2 comma -1/2 1. I mean -1 over d. This is not one -1/2. It's -1 over d, and you get this final matrix x, y, 0, and then 1 minus zd. Just write that down in your notes. We're gonna need that when we do the next example. Here, let me go up. So write all this down. Okay, let's move on to our final example. So our final example says, let S be the triangle 9, 3, 5. Let S be the triangle of the coordinate 9, 3, 5. X is your 9, Y is your 3, 5 is your Z, and then 12, 8, 2, and 1.8, comma 2.7, comma 1. Find the image of S under the perspective projection with the center of a projection at the point 0, 0, 10. Okay, so how would I set this up? So how you're going to set this up is you're going to do the image matrix, which was given, and then the projection matrix. And that gives you this. So your your image matrix was the the coordinates they give us. So remember, we're going across rows. Your x row, your y row, your z row. So it would be 9, 12, 1.8, and 0. And the next row would be 3, 8, 2.7, 0. And then the next row would be 5, 2, 1, 0. The next row would be 0, 0, 0, 1. And then the next matrix, the projection matrix would be this 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, negative 1/10, right? Because it was according to the rule, it's negative 1 over d, and our d was 10. And then this is 1. Okay, so when you multiply out those two matrices, you get this. You get 9, 12, 1.8, 3, 8, 2.7, 0, 0, 0, 1.5, 0.8, 0.9. So yeah, this entire row is your x coordinates. This entire row is your y coordinate. This entire row is your z coordinate. And this entire row is your perspective. Okay. So I'm going to circle this 9, 3, 12, 8, 1.8, 2.7, 1.5, 0.8, and 0.9. So what you're going to do next is take your XY pairs. You're going to take your XY pairs, that's why I circled those, and match them with what's happening with your eyeball. So your XY, so my X was 9, and then we're going to match it with your eyeball. So your eyeball was this. So these are your eyeball perspective, right? Your eyeball is your perspective. So it's going to be 9. So your first X coordinate is 9, and you're going to match it with what's happening with your eyeball. So it's 9 over the X coordinate for your eyeball is 1.5. And then the next one is 3, because you're 3. This is your Y coordinate over the perspective, which is 1.5. So we're still in 2D, and then it would be 12. The next one would be 12 over 0.8 because that's your perspective. And then it would be 8, comma 8 over 0.8. And then it's going to be 1.8 over the perspective 0.9. And the next one is 2.7 over 0.9. Something 3D got to be 2D on your screen. So yes, so note that something 3D got to be 2D on your screen. Makes sense, right? So like when you're watching this video, it's definitely 2D, right? So so the 3D coordinate 935 is going to be equal to 6, 2. Right, so how I got 6, 2 is I simplified 9 over 1.5 is 6, and then 3, 1.5 is 1.2. And then the 3D coordinate of 12, 8, 2 will be in a 2D coordinate, or or on the screen will be 15, 10. Basically, I simplified these ones. And then the 3D coordinate of 1.8, 2.7, 1 will be 2, 3. Okay, so yeah, that wraps it up for this lectures. It was all about simple, like just an introduction of application to computer graphics using matrices. Okay, so I'm going to stop here.